Imagine trying to construct every number and every mathematical operation from a state of absolute logical emptiness. In the late 19th century, this was the central goal of mathematical logic. Theorists wanted to derive the entirety of mathematics from a single unassailable starting point. Pioneers of this formal investigation in the 1870s, specifically Georg Cantor and Richard Dedekind, believed they had found that starting point. They turned to set theory. Loosely speaking, a set is simply a collection of items. Because the concept of a collection is so basic, it appeared to be the ideal bedrock for all mathematical thought. To make this system work, early theorists assumed that every conceivable collection could be treated as a valid set. But pushing this assumption to its logical limit reveals a flaw that causes the entire system to contradict itself. The attempt to build numbers from nothing resulted in a paradox that forced a change in how mathematicians define the boundaries of a set. To generate numbers using only set theory, we must begin with the single object the system provides for free. This is the empty set. By definition, it is a collection that contains 0 elements. In this framework, we use the empty set to represent the number 0. But to build the number 1, we need a new structure. The number 1 is created by wrapping a brand new set around our representation of 0. This creates a critical distinction. The empty set has no elements, but a set that contains the empty set has exactly 1 element. Because this outer set holds 1 item, it serves as the mathematical definition of the number 1. This process is recursive. To build the number 2, we follow the same mechanical logic. We take the representations for 0 and 1 and group them together inside a completely new set. This recursive nesting provides a formula for generating the natural numbers, using only the concept of sets within sets. Iterating this process indefinitely generates the complete spectrum of natural numbers. But numbers alone aren't enough. For a foundation to work, it must define how these numbers interact. Set theory provides these interactions through tools like the union of sets, which combines elements, or the intersection, which finds common ones. It also includes the Cartesian product, a method for combining sets to define relations. Using these operations, addition is defined as a set-theoretic combination of these nested structures. Multiplication is similarly derived from these operations, remaining entirely within the rules of the system. By showing how these basic rules of arithmetic emerge from set operations, early theorists believed they had confirmed that sets could serve as the bedrock for all of mathematics. Bertrand Russell, however, questioned whether this assumption of building sets from collections was actually logically sound. The system relied on set comprehension. This is a mechanism that allows you to pull elements from an existing set that satisfy a specific logical condition to build a new subset. Russell's critique focused on whether a set of all sets could exist as a valid mathematical object. If sets are objects, it seems valid to collect them all into one master set. Early versions of the theory allowed this unrestricted collection. But if you can apply set comprehension to a set of all sets, you can construct a subset that contradicts the rules of the system. Allowing set comprehension unrestricted access to every possible collection creates a logical loop that the system cannot resolve. To see the loop, we first assume that the set of all sets is a valid object. We then use set comprehension to pull a specific subset from that master collection. We define this subset S as the collection of all sets that do not contain themselves as an element. The entry condition is binary. A set is only included in S if it is not a member of itself. Now we ask, does the set S belong to set S? If we assume that S does belong to S, we hit a contradiction. If S is a member of itself, it fails the condition for the subset, which only accepts sets that do not contain themselves. Therefore, S cannot belong to itself. So we test the alternative. Assume that S does not belong to S. If S does not belong to itself, it now perfectly satisfies the entry condition we defined. Because it satisfies the condition, it must be included in the subset. This means S does belong to S. The set can neither be a member of itself, nor can it fail to be a member of itself. This is Russell's paradox. Ernst Zermelo independently discovered this same logical inconsistency at roughly the same time. This meant the system was inconsistent. Its own rules had generated a statement that was simultaneously true and false. The paradox showed that the starting assumption, that a set of all sets could exist was the error. This led to a new rule in mathematical logic. Not every collection of objects can be defined as a set. To handle these unrestricted collections, mathematicians introduced the concept of a class, which does not share the same properties as a set. Modern rigor requires that every new set must be constructed from sets that are already well-defined. Operations like set comprehension or Cartesian products must start from verified building blocks, such as the empty set. Mathematics no longer allows the top-down manufacturing of sets from unrestricted collections. This strict logical boundary is often overlooked in computer science, where collection and set are often used interchangeably. Enforcing this distinction between a set and a class allowed mathematicians to resolve the paradox and maintain the consistency of the logical foundation.